Hi, today we're going to look at the segment addition postulate. Recall a segment is part of a line that has two endpoints. It doesn't go past there. There is an invisible line that would extend through, but when we're talking about the segment, we're confined to those two endpoints. When a point is placed on the segment, we say it's between the two endpoints. So for example, if I want to place a point C, so it's on segment AB, I can place it anywhere along the segment. It doesn't have to go in the middle. It can go close to A, it can go close to B, it can go anywhere. When I'm asked to place a point between or on a segment, I generally will place it so that it doesn't appear to be a midpoint. Just in case I have to do some math with it, I don't want to forget that it might not be in the middle. Okay? Now, the next important thing to know is when you do have a point on the segment, that point divides the segment into two shorter parts. So I can see that this segment AB has been divided into segment AC and into segment CB. So a point on the segment divides the segment into two shorter segments. So this whole segment AB is divided into segment AC and segment CB. And these two segments are not necessarily equal to each other. Again, I can see here by the placement I did of C, AC would be shorter than CB, or at least appear that way. All right, let's talk about the segment addition postulate. A postulate is just a rule that makes sense. It doesn't have to be proven, so we won't have to prove the actual postulate itself. Okay? If point A is between R and M, so that means A is on the segment that connects these 2 points, then the distance from R to A plus the distance from A to M equals RM. Notice there's no segment bars over these, and so I didn't say segment RA and segment AM and segment RM. I said the distance from R to A, because without the segment bar, we're just thinking about the points. But remember, this word between means A is on the segment between these 2 points. So let's sketch a picture, because that's kind of a lot to kind of deal with without drawing a picture. So the first thing I'm going to do is I'm going to draw a segment that has endpoints R and A. So an R on one end and an an M on the other end, because it's between R and M. And then A is somewhere between. So it doesn't have to be in the middle. It can be close to R, it can be close to M. I like to put it close to one of the ends so I don't accidentally think it's a midpoint when it might not be. Okay? So my segment addition postulate says if I have a point on the segment, then RA, so the distance from R to A, however long this piece here is, plus AM, so plus this distance here, the distance from A to M, that's going to equal RM. So the distance from R to M. So if I take the green piece plus the pink piece, it equals the whole length, the purple piece. And that should kind of just make sense. I like to think of it like an ant walking along the segment. If I had a little ant on my paper and he walked to A, plus then he kept walking and walked to M, we could add those two lengths together to find out how far the ant walked total. Okay? And so I have a couple questions that actually kind of show exactly that. It says, what is the length of AC? So of segment AC. So if I look, I can see that this ant is going to have to walk 2.5 centimeters. Then he's going to have to walk another 5 centimeters. So we're going to have to take the distance that he walks for AB and the distance he walks for BC, and we're going to have to add those together to find out the whole length AC. So AB is 2.5 plus BC is 5 centimeters. So that's going to give me my whole length, which is 7.5. Okay, so when I come over here and I write my answer, I'm going to say that the distance from A to C is 7.5 centimeters. Again, notice it has the segment bar here. What is the length of the segment? But when I put my answer, I'm saying the distance from A to C is 7.5 centimeters, so I didn't need to write the bar on top. Okay, let's look at it a little different way. So this time, look at my ant. My ant has already walked part of the segment. And this is asking me, what is the length of YZ? So how far is it from just Y to Z? I know from before, if I take the first piece, my XY, plus my second piece, my YZ, it's going to equal the whole thing XZ. Now let's see, XY, we've already walked 5.5 centimeters. YZ, that's what I'm trying to find out. What is the length of that little segment just from Y to Z? XZ, I can see in my picture, is 10 centimeters. So if I want to know what YZ is, all I have to do is use my subtraction property of equality. So 0 plus YZ equals 10 minus 5.5, which is 4.5. And I know some of you didn't have to do that algebraically like I did it, but I like to show kind of the process of where everything comes from. I know some of you go, oh, I can just subtract. But I wanted to show you the algebra behind it of what's really happening there algebraically. For those of us who go, I never use math, but sometimes we do have to subtract, right? Think if you're going on a drive somewhere and you know the drive is 150 miles to another city and you go, okay, I've already driven 100. Okay, I have 50 left, right? Because you subtract 100 from 150. You're using algebra, right? You're just using a little bit more simply than writing it out expressly. So let's look at these two guided practice problems. I want to find the distance from J to L for the first one, and I want to find the distance from Q to R for the second one, okay? So what I'm going to do here is I'm just going to add, if I want to know the distance from J all the way to L, I can add the two individual pieces. So the left side, JK, plus the right side, KL, is going to give me the whole length of the segment. J to K is 8.4. K to L is 3.9. And I'm trying to find the whole thing JL. So I just have to add those two together and get 12.3 equals JL. And we can leave it just like this. If this was a proof and it wanted me to prove that JL equals 12.3, I'd need to use my symmetric property of equality to flip that around. Okay, let's zoom in a little bit on that green. It's a little difficult to see. Okay, so 12.3. When I look at the second one, I'm trying to find this side over here, the Q to R. I know if I take the two little pieces, my PQ plus my QR, it's going to equal the whole thing P to R. So now I've got fractions, and I know we don't like fractions, but I can use the calculator on my cell phone and just do 5 divided by 8. And when I do 5 divided by 8, I get 0.625. So that means this is 6.625. Plus QR, I don't know how long that is, equals PR. And PR is 13.3 or 13 3/4. 3 divided by 4 is like 3/4, so that's 0.75. So 13.75. And again, you could put that in your calculator on your phone or use a desktop one on your computer also to do that. So then this is the one where I have to subtract, right? Because I'm trying to find the little piece. So I'm going to subtract 6.625. When I do that, I'm going to get a 0 plus QR, which is just QR. I'm going to write it over here because I've run out of room. Equals on this side, oops, y'all can't see that. On this side, 13.75 minus 6.625 is 7.5. Oh, hold on, let me get that. I think I wrote that down wrong. 13.75, putting it in my phone calculator, minus 6.625 is 7.125. And my units here are feet. I forgot to put the units on the last one. That's not good of me. 7.125 feet. Okay? All right, in the next video, we'll explore how we can apply some algebra in these type of problems.